Hello, this is Minkowski. I'd like to talk today about cosmic redshift, which I believe is a required consequence of simple, plain vanilla general relativity. I've been looking at this topic for some time now, and I have some very interesting observations that I'd like to share with you. Redshift is a foundational assumption of cosmology. All objects in the universe appear to be moving away from each other, and the further away we look, the faster they appear to be moving away from us. This observation is based on an analysis of light that we receive, and the term redshift is derived by observing the spectrum of light from stars or galaxies, and then comparing that spectrum to a spectrum created in the laboratory. We observe that the wavelengths are stretched to longer and redder wavelengths. We see light arriving that is redshifted equally from all directions versus distance everywhere we look. So light equally redshifted from all directions. What can this mean? It could mean that the Earth is at the center of the universe. The Copernican principle asserts that humans are not privileged observers in the universe. Neither the Earth nor the solar system can be assumed to be at the center. It could mean that the universe is expanding in all directions equally. This is the hypothesis that was developed over a century ago and is the dominant paradigm in cosmology today. It could, however, be an optical effect caused by some subtle mechanism. In 1929, Fritz Zwicky proposed a tired light hypothesis. It was based on Compton scattering, which would have created blurry images, or worse, so much scattering that you couldn't see anything. No mechanism was developed to explain tired light, so it was kind of left in the dustbin of history. And Zwicky, at the end of his presentation, his paper, made a throwaway comment wondering about photon-photon interactions. He said, finally, it might be interesting to study the gravitational drag exerted by light upon light. And that was in the paper on the redshift of spectral lines through interstellar space, 1929. The current dominant explanation is that space itself is expanding. This assumes that all objects are relatively stationary in space and assumes that the space between the objects is what is expanding. Assumes that the further away we look, the more space that has been created. The concept of space effortlessly expanding seems to imply that little energy is needed to expand that space, and it seems to contradict the observations of the gravity waves that have been detected by LIGO. Gravity waves are created by sequential compressions in rarefactions of space, and based on these observations, space seems to be quite stiff and resistant to being stretched. Space seems to revert quickly back to its initial pre-disturbance steady state. So let's take a look at redshift as a Doppler effect. It's the classic explanation. At constant velocity, Doppler shift can be used to determine speed, but not distance. In this case here, we have a police car that's advancing to the left. There's shorter wavelengths as the sound waves are squished together, and behind the police car, they are stretched out, and they are traveling at a velocity v1. And they have a longer wavelengths for these recessional speeds. And the speed can be determined if the source wavelength is known. Under constant acceleration, relative distances can be inferred. In this case here in the top image, we have the listener who's behind the police car listening to the pitch at velocity 1. And we see that same location, velocity 1, in the lower image. But by the time we get to velocity 3, the police car has accelerated and that's stretched the wavelength even more. And you can tell from the pitch that you hear there how far away it is if you know the source pitch. So we can do a lot of inferring from the waves that we receive about the velocity. Light has an analogy to the pitch of a siren. Stars emit light, atoms absorb and or emit photons at specific wavelengths in the laboratory, and when light from a distant star passes through a prism, the components of light are separated into a spectrum based on their wavelengths. And in the case down here, I show light being broken up into its component parts, and I've identified a specific wavelength called hydrogen alpha. Here we're going to look at the redshift of a galaxy, one that is receding. In this case here, we have a spectrum on top, which is of the galaxy. It's compared to a laboratory spectrum below, and you can see that the hydrogen alpha line has been shifted to the right, to the redder side of the spectrum, indicating that the wavelengths have been stretched, and that is because it's receding away from us, either physically or because space itself is expanding. Edwin Hubble correlated Doppler shift with the distance to the stars at known distances. As you can see, there's a red line, and it shows that the recession velocity, the y-axis, is increasing with increasing distance. So the slope is known as Hubble's constant. It's a linear increase in velocity with distance, and the increase in velocity is an acceleration. So the universe is accelerating and has been known to be doing this since the 1920s of last century. What is causing this expansion of space? Observations do not support describing the Big Bang as an explosion. An explosion would provide an initial outward expansion followed by a slowing and potentially a subsequent contraction. Observations suggest greater recessional velocities at greater distances. Well, this is the opposite of gravitational attraction, pulling masses back together again, and it is in fact the Hubble law. Finally, observations in the 1990s suggested that the acceleration of the universe, the Hubble law, seems to be accelerating also, implying that there must be additional dark energy that is forcing this additional acceleration. So what about conservation of energy? Well, conservation of energy is central to Einstein's theory of general relativity. Einstein's stress energy tensor links all of the following to energy and gravity. So you have energy, mass, the famous E equals mc squared, temperature, pressure, momentum. They all have an attribute of energy. They all have an attribute of gravity. They're all attractive to each other. So there's a dual persona of energy, and that's gravity. Massive objects are effectively equivalent to compact blobs of energy. Light is bent as it passes by the gravity of massive objects. Light is bent by the energy associated with that blob. Again, the E equals mc squared. Due to reciprocity, the blob is equally affected by the light. It's a small effect, of course, but it's an effect that cannot be said doesn't exist. Massless objects such as photons have energy. The photon energy is E equals h nu. H is Planck's constant, and the nu is the frequency of the light. Energy and photons have this dual persona of gravity. Energy in photons is central to photovoltaic panels that convert energy, h nu, into electricity on many of our houses. So we all know that there is energy coming at us from light. The gravitational attraction between photons is an area of study. Potential distortion of lasers is the primary reason for that, and it's especially important in high-speed communications. In a classic paper from 1930, a year after Zwicky's paper, on the gravitational field produced by light, Richard, Tolman, and Bridge were the authors. This is an example of light being bent by a mass. This Einstein rings, and there's light from a galaxy that's far behind the cluster of galaxies in the foreground, and as the light from that galaxy comes towards us, it is bent and lensed and bent around so that we can now see the light, and it shows up this way as a ring. So let's talk about Minkowski space-time diagrams. We're going to talk about this concept quite a bit. We want to quantify when something can be known. This is a Minkowski diagram. It's showing past and future light cones. That's what we're going to be most interested in this discussion. 2 dimensions of space and 1 dimension of time are shown. The 3rd dimension of space is not included. You can see that there's a space dimension x and a space dimension y, and time goes up the vertical axis. So we have an event E, I've highlighted in red, that happens at the present time, and given an event E, the light cone classifies effects into one of 5 categories. You've got inside the cone, and those are events that can be affected by what actually happened at E. We have events, the events inside the past light cone can affect what happens at E. On the cone, you have the boundary of events for the future light cone or the past light cone. And on the outside, it contains all events that cannot affect or be affected by E without violating the speed of light. For example, if I'm at E and something happens a gazillion miles away, I can't know about it because that information can't get to me, or neither can I have an event here that will affect something a gazillion miles away. So it takes time to get that distance, and that's what this diagram basically shows. So now we're going to take a look at two light cones. They're going to have events at their center, and the event is the energy in the photon. In the green light cones, it's going to be h nu, and in the yellow one, it's going to be h nu prime. And before passing, neither of the photons can know about the energy in the other. That's because they are in their future light cones. They don't know that it exists. They may have known about the energy that ultimately would have created the photon, but not the energy in the photon itself. That's going to be a surprise when it ultimately passes by. And energy, of course, is the key common element in gravity. And as they cross each other, the photons pass into each other's past light cone, and their past light cones overlap. Events inside the overlapping past light cones can now affect each other. And after they pass, there's going to be an exchange of kinetic energy for gravitational potential energy between them. Energy in both photons gravitationally redshift each other, and the loss of kinetic energy results in a longer redshifted wavelength. So where did that energy come from? We'll take a look at that. The energy dynamics in the photons create a temporary asymmetry that can last an eternity. So here we have an atom with an excited electron. It's going to fall down to its lowest energy state. It's going to emit a photon with the energy h nu, and it's a vector. It's going with a magnitude and a direction. And because of conservation of energy, there has to be a recoil for the atom. The atom has to move in opposite direction, as I've shown with the vector r. And this has been demonstrated with the Mossbauer effect. The photon's energy is unknowable to anything to the right-hand side. So anything on the right-hand side is going to be surprised to see a photon coming at it. So let's take a look at a two-photon example. Here we have two atoms that are in their excited states. They both drop down, they both emit photons. They go in the opposite directions, as if this is coming from, say, a single source like the sun, or a star or galaxy, whatever. But they go in opposite directions, and as they are emitted, they create recoil energy in opposite directions, and those will cancel out inside the mass that created them, the star, and they can be effectively ignored. But if you're on the outside now, in this example here, we see the photons h nu and h nu prime going in opposite directions, but nothing outside them, their boundaries, their future light cones, can know that anything is going to be approaching them. In this case here, I've got two photons, A and A prime, and neither can be aware of the energy in those emitted photons until they pass by. So let's take a look at some light approaching the Earth. Here I've got my favorite little photon A. It's traveling along a red light beam. The light beam is gravitationally lensed by a galaxy, but it is approaching Earth. And as it's approaching the Earth, there's light traveling in the opposite direction, and as those photons in the countervailing flow approach and pass the photon A, they will begin to exchange gravitational energy and kinetic energy, and that will be the source of some redshifting. So let's talk about the passing of spheres of lights, which will exchange energy without distortion. So here we're going to look at approaching photons that are each unaware of each other. The approaching photon A is not aware of the approaching photon sphere, and the approaching photon sphere is not aware of the approaching photon A. After passing, photon A loses kinetic energy and gains gravitational potential energy. Photon A has become redshifted, and the photon sphere has also become redshifted by this single photon. So here we have two spherical fronts of photons that are approaching each other. Both are unaware of each other. The red photon sphere is not aware of the approaching brown photon sphere, and the brown photon sphere is not aware of the approaching red photon sphere. Once they pass, however, and they enter in each other's past light cones, all the photons will exchange their kinetic energy and gravitational potential energy. The red photon sphere will become redshifted. The brown photon sphere will also become redshifted. And there'll be no distortion in these spherical photons interactions. In other words, no Compton scattering. So the energy exchange here is gravitational for kinetic energy. It agrees with the conservation of energy. It agrees with Einstein's general relativity. The exchange explains redshift, and the redshift would appear to be the same in all directions, no preferred direction. Magnitude of the redshift would depend on the amount of the oncoming flux that was encountered. This mechanism will not create scattering, blurring, or distortion, and it suggests that the long-held postulate of space itself expanding is probably wrong and is at least incomplete. So let's take a look at a couple of energy exchange examples. I'm going to use baseballs, asteroids, and a rubber sheet analogy. In this case, I've thrown a baseball. It's going to have exactly the correct amount of escape velocity. The baseball, in this case, will be slightly attracted to an approaching asteroid. The effect of gravity is transmitted at the speed of light, and the three objects will be all aware of each other. The warping of space-time enables both the baseball and the asteroid to accelerate towards each other. The baseball will be accelerated to slightly greater than the escape velocity at this time. The gravitational effect of the combined Earth plus asteroid, once they merge, will be sufficient to decelerate the baseball to exactly the escape velocity again, and illustrates the conservation of energy because everything was aware of each other. And here we're going to repeat the example using a rubber sheet analogy. The baseball has the exact escape velocity. The baseball will be decelerated as it moves away from the Earth and accelerated towards the asteroid. After the asteroid passes the baseball, both the Earth and the asteroid will decelerate the baseball. The baseball will revert to its exact escape velocity, and the net effect of the asteroid will have been canceled out. However, using the rubber sheet analogy for two photons that are approaching, what we know here is that the brown sphere of light cannot be aware of the approaching red sphere of light because they're traveling at the speed of light towards each other. And so the brown sphere has no sense of what lays ahead. Likewise, the red photon sphere has no sense of what lays ahead of it, and it's only aware of its own energy and gravity. After passing, both have each other's energy and gravity in their past light cones. Now each needs to climb out of a slightly higher gravity well in its past. A higher gravity well is what creates the redshift effect. So what we have here is a police car that's going up a hill out of a gravity well, and it doesn't have any sense of what's coming at it, doesn't know that the brown photon sphere is coming at it, and the photon sphere doesn't know that the police car is ahead, but eventually they will pass, and once they've passed, the photon sphere will now be, well, we'll just say it's been redshifted, and it'll probably hit something, and its mass will end up on a rock someplace, I don't know. But this will create a slightly higher, steeper gravity well for the police car to climb out of. It's probably not a perfect analogy, but it's an analogy all the same. So now let's add another dimension to this discussion. The energy exchange can't come from behind. The photons from behind are also traveling at the speed of light. So what we have here is we have a cluster of galaxies on the right, we have photon spheres emitted by them, and on the left-hand side there's a countervailing photon sphere that's going to be passing the Earth. As the photon spheres pass, their past light cones overlap. The photons lose kinetic energy in exchange for gravitational energy, and they become redshifted. Light from distant galaxies, as seen from the Earth now, have become redshifted. The same effect would be seen from every direction. This is because the energy exchange can't come from behind. So can any of this be validated? All hypotheses need to have some validation to remain viable. It's probably unable to observe gravitational redshift in an Earth-scale laboratory. Absence of evidence, however, is not evidence of absence. So cosmic redshift is a feature that's associated with immense distances. The Hubble constant is an acceleration, which is an increase in velocity per unit time of 70 kilometers per second per megaparsec. This is equivalent to 6.8 times 10 to the minus 10 meters per second, and that's compared to 9.8 meters per second of gravity here on the Earth at about sea level. The increase in the wavelength per megaparsec against the countervailing flux in the universe is 1.000233 per megaparsec. Because a megaparsec is 3.08 times 10 to the 22nd meters, the per meter value may be too small to measure. But there are potentially two ways that you could validate this. The first one is by experiment, and that would be using interferometry to see if countervailing photons from a laser could create a detectable increase in the redshift from a star. A possible second validation would be observational, and that's a large energetic event from something like a supernova that might create a detectable effect, an increase in redshift. In this case here I have two telescopes from a very large telescope array, number 1 and number 2. I have a laser. The laser is going to emit a pulse up towards star A, our target star, and the VLTs are looking also at this target star A. And the Earth is going to be rotating, so the laser pulse will go up, the Earth will rotate, and as the light beam that has been created from the laser pulse mixes with the incoming light, there may be a redshift that is detectable from this, from the gravitational and kinetic exchange of energy of the laser and the incoming light from target star A. In this case here, you would see a small change in the interferometry between them for a brief moment as the laser pulses were aligned with the incoming light. This could also be validated by observations. So we're going to assume that there's a supernova that can create a powerful countervailing flow of photons, and it's additional flux against the incoming photons from that more distant galaxy. Then the redshift of the more distant galaxy, if it was recorded before the supernova, and if that object could be identified now, its redshift could be compared to see if there was any changes. A post-supernova observation may be slightly more redshifted. So this is an example. We've got Earth, we've got a distant galaxy, and we've got an unremarkable star E in the middle. Once the unremarkable star E goes supernova, it's going to create a large source of photons that are going to go in all directions, including towards the distant galaxy with the redshift Z. Once these spheres of photons cross each other, they're going to enter each other's past light cones and will then begin to exchange gravitational energy for their kinetic energy, and the redshift that should be observed from the distant galaxy should be Z plus a small change delta Z. So if this is an observable phenomena, this could possibly explain a number of observations. There could be pockets of increased redshift from these countervailing photons, and the normal redshift between the pockets would be slightly different. And if the countervailing photons from these high energy events can create these local variations, that may explain things like variations around, well, say supernova versus redshift, cosmic microwave background variations. The variations could be caused by events that occurred in the distant past for which no trace remains or which has migrated to a different location in the sky. And of course, the expanding space concept cannot create this kind of variation. Because I mentioned the cosmic microwave background, I thought I should give you a few reasons why I have not included it. There's two reasons that I've identified here. First, the signal to noise of the 2.7K spectrum from the Cobe-Ferris horn is incredibly powerful and distortion free. The error bars need to be scaled up by a factor of 400 just to be seen, and it suggests a source that's proximal to where it was measured and not something that's been coming across the entire universe and distortion free for all these billions of years. The 2.7K spectrum was also not validated at any large distance. It has only been measured in the vicinity of Earth. Neither the WMAP nor Planck satellites measured the spectrum at L2. The WMAP spectrum was not designed to measure the 2.7K spectrum. WMAP was designed to measure only the differences. The Planck satellite was technically capable, but did not report the 2.7K spectrum. Bolometers in absolute mode were capable of validating the spectrum, and the powerful noise-free signal inferred from Cobe in near-Earth orbit should have been easily verifiable. So in conclusion, an explanation for cosmic redshift has been proposed that is consistent with observations. Similar redshift versus distance in all directions. Redshift would be linear with distance, assuming a constant countervailing flux in the universe. Neither regions of high density nor voids would affect the redshift. That was one of the reasons why tired light was not considered. No blurring or distortion. It's consistent with the conservation of energy. The key physics underlying this hypothesis is that a temporary asymmetry is created due to the speed that energy can travel, and the asymmetry is caused by the energy suddenly appearing in a photon's past light cone, and this asymmetry is observer dependent, depending on their inertial reference frame. This hypothesis may explain the observed redshift, or only a portion of it. Thanks for watching, and let me know what your thoughts are in the comments section below. And if you've heard this particular hypothesis presented before, let me know. I haven't been able to find it, and I would very much appreciate that. Again, thank you for watching.